Good afternoon, everyone. Thanks for joining again this week. I'm just about to start the webinar for thermal stability techniques, summarizing some of the screening techniques we have through to adiabatic calorimetry for more sensitive results. I'm just going to hold on a couple more minutes for anyone else to join us in the meantime. Okay, good afternoon, everyone. We've got a couple more people here now, so I'll introduce the webinar properly. My name is Dr. Ollie Armstrong, working here at Sigma-HSE in the Chemical Process Evaluation Lab. The webinar today, we're going to cover all things thermal stability in regards to chemical reaction hazards, from sort of the quick and easy indicative screening tests through to more advanced adiabatic calorimetry tests. Some of the later techniques or equipment we'll be using are very adaptable, but we'll try and focus on particularly thermal stability and how it fits into your kind of process safety design for your chemical reactions. So again, thanks for joining. The start of this webinar, just a bit of an overview. We've got kind of 4 questions which should help us set out what exactly is thermal stability issues in regards to chemical reaction hazards, why the analysis of these hazards are required, and the relevance to your process. when chemical reaction hazards analysis is needed or recommended, and also which techniques are available to help you assess your process during scale up and redesign. If anyone does have any questions as we go through the topics in the slides today, you can enter it in the chat function in the webinar system. Put them in at any time. If there's a specific slide you want to reference to, just include that in the message and we'll respond to those queries later on. So as I said, the objectives today, hopefully at the end of this, we'll have a better understanding of thermal stability as a phrase, how it relates to chemical reaction hazards, and exactly this encompasses. Secondly, why understanding thermal stability is sort of a key factor to designing your process safely. What kind of thermal stability screening tests there are, and also the adiabatic tests, and then how some of the testing and the outcomes and the data are relevant to your process and how they should be applied. So a bit more about Sigma-HSE, what we do and where we are. So I'm based in Winchester, UK, which is our main technical office. We've got also technical offices based in India and in the US, where we've got consultant teams in all those places. And we have our main testing laboratory, including our CRH lab in Winchester. And we also have a process safety testing lab in India, which at the moment is based on sort of dust combustibility testing. So as we've sort of outlined a little bit, we're covering across these 3 continents to provide our clients with advisory services and appropriate engineering solutions so that people can improve their process safety. And we undertake our laboratory testing in our UK labs following ISO, BSI and ASTM standards where possible, particularly in regards to thermal stability testing that we'll be doing today. There's some ASTM standards which we can follow. So we've got quite a range of specifically process safety testing that we do here in Winchester, and as I said, some of it we can all do in India. Of most relevance today, I guess, is our chemical reaction hazard testing or process evaluation testing. Our thermal stability testing, and that phrase can be a little confusing because it does apply to our chemical reaction hazards testing block, but then there is also thermal stability testing to do with UN regulations for transport and storage. We will be focusing on thermal stability in regards to reaction hazards today, but the stability and transport testing is something we can help with as well. As I said, we have our fire and explosion properties, our dust testing. We also have gas and vapor testing. There's a nice image there of upper flammability limits testing and electrostatic properties testing as well. Again, all of these testing sort of brackets are focused on process safety testing. And as I highlighted before, our consultancy services provide a wide range of specialist technical and quite a wide range of topics. Some of our consultants have specialist areas, but we're able to cover quite a range of sectors really. And again, it depends on whether we're doing DESIR or ATEX, whether we're operating in or out of Europe, in the US, in Asia. They need to be mindful of the local regulations. and our offering with testing and consultancy can often come hand in hand. Some of the consultants' reports will require some of our testing to give more certainty about the hazards of a process. So now getting into the bulk of our webinar today, what are chemical reaction hazards, specifically thermal stability issues. So many of our desired chemical reactions will have inherent risk of exothermic decompositions. It's just a matter of fact that some of our reagents may be thermally unstable. Obviously, we always try and design out hazards, but sometimes these are unavoidable. So our decompositions often are exothermic and may also produce gaseous products. So decompositions will tend to produce the most stable compounds, which can often be gaseous. Decompositions in a reaction mass can also trigger further decompositions potentially, or produce toxic compounds which we'll want to control the release of. In terms of these reactions being hazards to our process, the exothermic energy and permanent gas generations have the highest risk potential. We'll go into that a bit further later on. Full knowledge of a process at scale is required to ensure safety and loss prevention. So this is how and why our kind of thermal stability testing is important for process scale up and design. Just the understanding of how some of these phenomena change from laboratory R&D scale to large scale and bulk. So finally, runaway reactions have caused a number of industrial incidents over the years. And these runaway reactions tend to be caused by decompositions triggered by failings of a desired process. And again, we'll talk a bit about that kind of mechanism later on in the application of the data. So we've got some key definitions here relating to thermal stability hazards. So causes of overpressurization. This is kind of one of the key hazards from secondary decompositions. Heat of reaction or heat of decomposition as a measure of how much energy is given out by a reaction or decomposition. The adiabatic temperature rise, that helps us describe how energy is retained within a system when we're translating from a small scale reaction to a material or reaction in bulk. The Arrhenius relationship, so that's kind of linked to how as temperature rises, the rate of reaction is also going to increase. So we get an exponential relationship. Thermal runaway, as I've talked about this before, this is kind of where a kind of desired process, which may be out of control, is giving out a mild amount of heat, but then this can then trigger a secondary decomposition reaction, which can run wildly out of control. Phi factor, again, this is something else important to understand, the difference between tests performed at small scale to large, and it's kind of a correcting factor. Heat losses, again, this is about how things translate from small scale to large. Reagent accumulation, so potential causes of thermal runaway as well. Onset temperatures, so this is going to be an important one for the differences between quick screening tests and also adiabatic tests. Safety factors, again, that is kind of a key difference between the screening tests and the adiabatic tests. And then also a little bit to do with flow regime and venting, emergency relief systems. So as we mentioned back then, pressure is kind of a key hazard when we're thinking about a reactor which might have containment of a reaction system. So if we have a decomposition, rarely will exothermic energy alone be a hazard by itself. You know, a lot of these reactors would be able to deal with an increase in temperature and let the reaction or decomposition kind of run out. The additional issue of pressure is where we can have tank ruptures, which is much more dangerous. So the effects of pressure increases on a system can be much more crucial. Overpressure can come from three potential sources. So the first one is we can have gas generation from the normal process. So we can have a byproduct or a product of a desired reaction, which is actually a gas, and that's going to, if it is contained, that's going to give us a pressure increase. Number two is vapor pressure effects. So again, that can be from the normal desired process. If we're increasing the reactor temperature, you're going to have an increase in vapor pressure as well. This is less of a hazard because if your reactor returns to standard temperatures and pressures, the vapor is just going to condense again, and that pressure issue is nullified at that point. But step three, which is more pertinent to today's discussion about thermal stability, is heat from the normal process causing a secondary reaction or a decomposition. So that's the kind of thermal runaway scenario mentioned before. And that secondary reaction or decomposition is itself generating gas, and in turn is also going to increase vapor pressure as the temperature increases. So this plot here is called an Antoine plot, and we use this quite commonly with especially one of our screening tests, but we'll come to that later. So as we've got a contained system, this is just a way of kind of entangling the data and seeing where we have vapor being formed as the temperature increases, but then also when as an indication of when a decomposition is occurring, which is actually producing permanent gases. So the way we do this is via a log plot of the vapor pressure tends to scale linearly with the inverse of the temperature. So you can see at the bottom right of the graph, the line there is quite straight as the temperature is increasing from right to left. And we've marked on a kind of onset point where we can see the line curve away from this trend, and the pressure is increasing much more quickly. So that kind of shows us that at this purple dashed line, we've got the start of gas generation at that temperature point. So that's kind of, those past slides were kind of telling us about some of the ways these incidents can get out of control, just to sort of lay out sort of the variety of different causes and scenarios in which these incidents can occur. There's been some different surveys over the years. We've picked out a UK example here from the HSE, and it just shows the variety of different industries which can report incidents from thermal runaways or loss of control scenarios. And as we can see, there's quite a list of different reasons for or causations given for why these runaway reactions occurred. Up there at the top is the mischarging of reactants. So we can understand that if we're normally dosing a reagent in to maybe control a desired exotherm within tolerable levels, if for some reason a whole batch is added in one go, that's that's going to fail our controls and increase the temperature above where we wanted it to be, which could trigger another decomposition and a thermal runaway. Lack of thermochemical knowledge, inadequate temperature controls, inadequate maintenance, inadequate agitation. So agitation kind of comes back to those reagent accumulation. That was one of the keywords at the front. Raw material quality, impurities getting into the system and causing a secondary reaction, operator error, or uncategorized reasons. So there's quite a range of causations that can lead to these runaway scenarios. And these can kind of be categorized into an improper assessment or design based on the differences of scale up. So as we've sort of explained before, the differences between running a reaction at lab scale during research and development is going to be quite different to at bulk, and that's typically regarding heat losses at bulk is the main difference. So the subpoint there, heating and cooling requirements can vary exponentially with batch scale. And also what can come under improper assessment is if the reactor is only designed around normal operation, so just dealing with heat output from the desired reaction, but not considering worst case scenarios, which is when our kind of thermal stability screening is coming in. That's looking at the worst case scenario and potential decompositions. These aren't the reactions we want to happen, but we need to be cognizant of what does happen if they do occur. Secondary to that is kind of systems failure. So we talked about maintenance, failure of equipment or supply systems. These can all cause issues on reactors. And then, of course, process failure, mischarging of reagents, operator errors, incorrect information for the reaction, lack of training, all these kind of things come under process failure. So why is the analysis of CRH required? This table here just gives us a bit of an indication of a range of decomposition energies for different functional groups. So we can see down there at the bottom, a lot of the high energy decompositions, they're tending to contain nitrogen groups. So generally, if we see any of these functional groups in materials that we're scoping for clients, we'll advise thermal stability testing. And again, it just, these kind of literature values can help us really hone in on what are the riskiest parts of a synthesis method. So as I've been harping on a little bit with the differences of scale, how it changes from small scale reactions to large. As volume increases, the relative surface area decreases. It's an unavoidable. The effective cooling capacity of a reactor is linked to the surface area. Typically, if we imagine a cooling jacket on a reactor, that's all about the interface of the reactor wall and the cooling fluid in the jacket. Heat removal capacity is only linear, and that's linked to the cooling medium used in the jacket. Whereas heat generation at scale is exponential, and that is considering the adiabatic nature of bulk and also the Arrhenius equation, as we discussed before. As temperature increases, the rate of the reaction is also increasing. So a runaway reaction is only going to get hotter quicker as time goes on until it exhausts itself. So this relationship can lead to a runaway where the cooling of a reactor is no longer capable of treating or removing the heat from a system. So we can see the red line, our green dotted line is our heat removal due to our jacket, and as we said, that is linear which is linked to the heat removal medium. And then we've got the maroon line, which is as temperature is increasing, the heat removable requirement is also increasing. And when we reach the critical temperature, the heat being output from the system is overdoing the heat removal due to the cooling. So the system at this point is only going to generate and output more and more heat as the reaction goes on. And this is leading to a thermal runaway. So just to illustrate quickly the differences of scale, it's a good indicator if we take a 10 ml test tube, if the liquid within the test tube is at 80 degrees, it'll take 11 seconds for it to drop to 79 degrees, so dropping 1 degree Celsius. As we scale this up to a 100 ml beaker, the same temperature drop would take 17 seconds. And you can see as you increase the reactor volume and mass, it is only scaling up and up. So a 25-ton reactor would take 233 minutes to drop 1 degree Celsius. So a full understanding of the chemistry you're performing and the plant you are using will help you understand fully what the impacts are of any potential process deviations. Some of the techniques and methods below are available for hazard risk and consequence assessment, such as HAZOP, computer HAZOP, what-if analysis, FMEA, and others, just to really think through the steps of, if I change this about my process, what could be the potential impacts. So as we've said, when is analysis of CRH requirement? This kind of thermal stability and adiabatic calorimetry testing fits in well in sort of the later stages of R&D, when you have a material you want to make, you've got some, you might potentially have some synthetic routes identified. That's a good time to start thinking about thermal screening testing to give you an indication of any potential hazards for when you scale up. And then adiabatic calorimetry kind of becomes more important when you've got a specific synthetic route that you want to go down. And it's good to have this data before you scale up or during when you scale up to pilot plant scale. But it's definitely data that you need before you take to bulk production scale. So again, this kind of links in our kind of screening techniques, as we call them, tend to be with the DSC, the differential scanning calorimeter. And as we saw on the previous graph, this is very good for very early stage R&D testing, just because it's very small sample requirements. 10 milligram or so is normal. And it gives a good indication of material stability at elevated temperatures. Later on in our screening testing, we have the carrier's tube. So this does need a larger sample size of 10 milligram. Sorry, I'll just go back. Of about 10 grams, sorry. So this tends to come later on in R&D stages when there's more material to spare. But the carrier's tube does give pressure data, which the DSC doesn't. So it's a good indicator of potential requirements for vent sizing data for reactor design. And then moving on later into the process to our adiabatic techniques. So for example, here we've listed the ARC test. And again, this has a moderate sample size requirement, but it is much more precise in terms of its exothermic onset with that 30-degree safety factor, whereas you can see higher up with the DSC, it's about 100-degree safety factor. So it just gives you more certainty around when exactly you might have issues with decomposition. So which techniques are available? As we've sort of outlined, there's various equipment and techniques, and these really need to be tailored to the specific process needs and contexts. We've got our thermal stability screening tests, and also our adiabatic tests. These will also link in with any reaction calorimetry data that we have, and we'll see how that applies to the process a bit later on. Also, when we're thinking about these techniques, 5-factor is really a key consideration when looking at the results. So 5-factor, as I sort of said before, it's a good correction factor for considering our data from small scale tests and how that might apply to a large scale system. So we need to understand that heat generated within a reaction mass is consumed in 3 ways. So that is firstly to raise the temperature of the reaction mass itself, and this is linked to the scale, the size of the reaction mass, but also the specific heat capacity. Secondly, to raise the temperature of the reactor walls, and again that depends on the materials of construction and the heat capacity. And finally, any heat losses to the environment and the surrounding environment. So as the vessel size changes, the relative effect of reactor cooling also changes, as we discussed before in cooling capacity. So 5-factor, a simple correction factor for these tests. If we understand that a infinitely large reactor is going to have a 5-factor of 1, because there's going to be no effect of the container, because the mass of the reactor material is going to be the majority of the system. So 5-factor is just 1 plus the mass of the container times the heat capacity of the container, divided by the mass of the sample times the heat capacity of the sample. So as a good guide here, we've got our carrier's tube screening test. The 5-factor in that case is going to be about 2.5 at best, up to 4, 5-factor. Again, that really is dependent on the nature of the material you're testing and the heat capacity of the material, because that can range from 0.5 through to 4 or 5. So that really has a big influence on the 5-factor. Secondly, one of the adiabatic tests, we've got the ARC, and that is at best 1.5, but again, typically it's more around 2.5, 3. And then at the bottom, we've got pressure compensation calorimetry. So that covers our ARSST, VSP2 testing in open cell configuration. And that's about as good as you can get for sort of lab scale thermal stability assessment testing. And that is 5-factor of 1.05. As another example, if we were to consider 5-factor for the DSC test, the 5-factor would be close to infinite, because the mass of the container, say it's about 1.2 grams, when we're putting a massive sample into that container of only 10 milligram, the mass of the system is much more weighed towards the container. So when we're looking at 5-factor, DSC looks very bad, but it is still a very good screening technique to give indications of thermal stability issues. So the consequences of different 5-factors, if we consider a high 5-factor system, such as the carrier's tube, the DSC, if we have a decomposition over time, there's going to be greater heat losses to the container. And as this plot shows, the dotted line, we may not hit a secondary decomposition because there's been heat loss from the system. The heat hasn't been retained wholly within the system. So that is most likely to be captured in a low-fi system. As you can see, the burgundy line, we have an exotherm, it plateaus again, but then we hit a secondary decomposition exotherm. So that just relates the importance of low-fi systems and adiabatic systems. So screening and thermal stability, these tests are typified potentially low sample requirements, specifically for the DSC testing, speed of results. Again, that's kind of why we categorize it as screening tests, especially some R&D labs within companies. If they're doing testing in-house, you can screen a large number of compounds within a small amount of time, especially with the DSC. As we've said before, this is kind of indicative of more accurate testing. It's just to highlight whether you may have any potential thermostability issues and whether there's anything worth investigating further and in more depth later. These are lower accuracy techniques than some of the adiabatic techniques. That's not to say that the test methods themselves aren't accurate because we're following ASTM standards or other literature methods. It is just that we have to apply a larger safety factor to the onset temperatures due to these considerations such as higher phi factor. These screening tests can also have pressure data, so that's where we would use our Carrier's tube for the pressure data. And as we've said, the regions of interest can then be studied in adiabatic methods. But these take more time and effort to conduct. So these tend to come later on in a process development timeline, which is where we move into adiabatic calorimetry, specifically to do with thermal stability. These can be typified by an increased sample requirement. So the ARC and the ARSST, we can test materials of about 5 to 10 grams. If you take anything to VSP2 or Phytech, you're talking hundreds of grams. But because of these larger sample size, it is easier to generate more representative samples of heterogeneous mixtures if we're testing reaction masses from actual chemical reactions rather than pure compounds only. It is also easier to mimic reactor conditions using these equipment because we can quite often have different stirring and other kind of reactor conditions to make it more applicable to your process rather than just having a constant temperature ramp. We also have pressure data at this point, which, as we've outlined, is very important when we're considering thermal stability. And these techniques have greater accuracy and a confidence in the results due to the lower phi factor, the adiabatic nature of the testing. But again, these are not screening tests because they can take days to run per test with setup time and analysis. Yeah, so there's a bit of a trade-off there. And all of this data kind of feeds into when we're evaluating a whole chemical reaction process, the reaction calorimetry. So as we've outlined before, kind of the potential for a thermal runaway is typically triggered by something going wrong with the normal desired reaction, which is where our reaction calorimetry comes in, then triggering a secondary decomposition, which is where our thermal stability testing comes in. So our reaction calorimetry methods can be done at different scales. So these can be done at roughly 5 grams to a litre scale. The methods have to be designed bespoke based on the process under evaluation and just getting the reaction conditions as close as possible to those that will be on plant. They are very accurate systems used to ascertain various plant condition requirements. So these can be used for dosing rates, stirring requirements, all sorts of different parameters for reactions. And these can also, again, be typified by longer run times, and these can take a couple of days or more depending on the reaction. So as we've said before, these can be used to simulate various conditions and optimize your process. When we're talking about designing to the worst case as well, the reaction calorimetry can be performed specifically when it comes to emergency relief systems and things like the VSP2 and the FITEC. You can test scenarios such as fire exposure to a reactor or reagent mischarging. You can test all of those scenarios and design the reactor to the worst case for the safest possible operating envelope. So diving into the equipment we have here at Sigma-HSE now, as we started with the thermal stability screening tests, the DSC, most people will be familiar with. So they have a extremely small sample required. It depends on the activity of the material, but it's going to be in the range normally of 2 to 10 milligrams per run. It is very fast testing. It can take 2 to 4 hours, which is relatively very fast. It gives us a breadth of data, very good indicative data of energetic events, whether that be exothermal, but then also endothermal, such as phase transitions, morphological transitions. So yeah, it's good for screening decompositions, but also reaction temperatures. Again, this is a lower accuracy system with a high phi factor test, but it is widely used and understood, and there's lots of literature data out there to reference against. So there is 2 ASTM standards which we can follow for DSC testing. There's the ASTM E517, which is regarding chemical material stability, thermal stability, and then the E2160, which is more about reactivity and judging what kind of temperature set point reactions are occurring the most at. And we can also judge sort of curing temperatures of polymers and things using this method. So in terms of thermal stability for process safety testing, DSC testing is best performed in high pressure sealed ink alloy crucibles. So the ink alloy has a very good compatibility with a range of normally corrosive materials. A lot of DSC testing is done in alumina or gold open pans, but for our process safety assessment, it is best to have sealed high pressure crucibles, just to make sure we're not losing any energy in the system through vaporization or gas losses. So the principle of the DSC is that the sample pan is measured against a reference pan. Both of these are heated up equally with equal energies, and the differences in the heat of both sides of the balance are weighed against each other, and that kind of gives us the heat output of the sample at different temperatures. So as we've said, the heating is applied in an insulated oven. Although it's a screening technique, it is a very sensitive technique in terms of the actual makeup of the instrument and how it works. So it's a very sensitive and robust instrument for high throughput. As we said, it's a very good screening technique for running lots of samples quickly. So the Carius tube is next. As we said, this is still a screening test to us, but there is a higher sample amount required. We aim for around 10 gram, 10 mil of material, but it really depends on what the system is. We can do some explosive screening testing in the Carius tube, and there's a published AstraZeneca paper which recommends using about 3 gram in a Carius tube. So it really depends on specifically what testing we're looking at. The main condition of the amount of sample needed for the carrier's tube is that we cover the thermocouple at the bottom of the vessel to know that we're measuring the sample temperature. So using this greater sample size is much more representative of heterogeneous mixtures. Relatively fast testing, so it can take about 12 hours to run a sample. It's good at indicating energetic events in terms of exotherms and endotherms. So similar to the DSV decomposition, exothermic decompositions, but also melting points, things like that will pick up. But it is also, the way it's different to the DSC is that we can use the pressure data from a carrier's tube, which is helpful. We tend to use the Antoine plot that we discussed before to provide an onset of when we think gas generation is being formed in the decomposition, rather than just the vapor pressure increasing as the temperature increases. Again, this is a lower accuracy test with a relatively high phi factor. That's another reason we want to use quite a large amount of sample in here, is to try and lower that phi factor. This is an industry standard test, the carrier's tube. It was developed early on in ICI and AstraZeneca, and it's held its relevance in the European market at least. So just to see the internals of it a bit, we have our sample loaded into the carrier's tube, where we have a thermocouple reading the temperature of the sample. We also have another thermocouple in the oven, and it is a differential temperature measurement that's taken between the sample and the oven, the programmed oven. We also have that pressure data recorded, which is plotted alongside that differential temperature. Produced gases can be sampled from the system, and they can be analysed with things like GCMS, so you can know what exactly in your mixture has broken down, what it's formed, what the hazards are potentially of those gases and vapours as well. And the larger the sample, again, the more representative the test can be of sort of complex mixtures, those with minority catalysts present, or solid solvent mixtures. It's much easier to test in the carrier's tube to be representative. Moving on to some of our adiabatic techniques now. So we've got the accelerating rate calorimeter, the ARC. This is still quite a small sample size required, so 3 to 5 grams. Again, the higher sample amount we can put in, the lower the phi factor will be. But again, this isn't always possible depending on what the client has available. This is a slow test because of the heat weight search method that it uses. So this can take 3 days to complete a test. But the heat weight search method does give very accurate onset temperatures for thermal decompositions. So a safety factor of an ARC test might be 20-30 degrees, whereas with a DSC, it's up to 100 degrees. So it's slower, but it gives much more accurate data in terms of bulk system hazards. So it also has pressurized data as well as the temperature, adiabatic temperature rise, and also sort of kinetics data it can analyze, and temperature rise rate and pressure rise rate can be used. So it is a higher accuracy test than the thermal screening methods. It's got a medium phi factor of around 2.5 to 4 is typical. And again, we have an ASTM method here of ASTM E1981, and that is regarding the thermal stability of chemicals. So the principle of the ARC, and the reason it is an adiabatic test, is that we have a metallic bomb suspended within an oven, and there is a thermocouple which measures the sample material temperature directly. and that heat weight search mode that I've talked about, it'll increase by 5 degrees and it'll hold at that temperature for 30 minutes, 60 minutes, and it can detect a temperature rise rate within the material of, say, 0.02 degrees per minute. So there's very slow temperature rise rates there. It can pick those up and it will match the oven temp to the temperature inside the test vessel. So that is mimicking sort of the zero heat loss scenario, such as an adiabatic system. So it is performed in a closed cell bomb, as it has to deal with potentially high pressure decompositions. That's why it's made of metal. But the downside to this is that that's what makes it potentially a high 5-factor system, because the bomb has to be made of metal. It's quite a dense test vessel, and it's hard to get that 5-factor very low. But it does still give very accurate onset temperatures for exothermic information. We typically use the titanium alloy, but there are different materials out there: Hastelloy C, stainless steel. There are also glass bombs, but they aren't able to withstand anything like the pressure increases that the alloy ones are. Moving on to the Advanced Reactive Systems Screening Tool, the ARSST. So this is slightly larger sample requirements than the ARC, but slightly less than the Carrier's tube. We've got a 10 ml glass vessel, which we're looking to fill up. So we'll normally use about 7-8 grams of material. It is a lot faster testing than the ARC, and it can be, just for thermal stability analysis, it can be about 4 hours per sample. That would be typically in a constant ramping mode, which again kind of reflects the Carrier's or the DSC, where we've got a constant temperature ramp. The ARSST is very good for gassy decompositions or reactions that require tempering or inerting with nitrogen to sort of simulate your reactor conditions. If we've got sort of oxygen sensitive materials in there. And again, it can give a wide range of data: pressure generation, adiabatic temperature rise, and the origins of this ARSST is it was kind of designed for deers in the States, and that it was kind of designed to give basic sort of vent sizing and emergency relief system data. So that's the temperature and the pressure rise rate. Those are kind of typical outputs from the ARSST. We can also do basic reaction calorimetry in the ARSST, but other methods are better for that kind of testing. Again, it's a higher accuracy test than the screening tests. It has a very low 5-factor, and that's just down to how it works, which we'll show a bit more in the next slide here. So there is a sort of 330 ml or so steel container. Within that, we use a 10 ml glass vessel, which is very low weight. So we think back to the 5-factor equation. Having that very low weight glass vessel, we can then load in much more mass of our sample material, and the 5-factor equation is skewed much more towards the mass and the heat capacity of the sample rather than the container it's within. So that's only relevant when we're testing in the open cell function, and that is the preferred mode for ARSST, especially for gassy systems. If we start doing closed cell testing in the ARSST, it's basically going to function similarly to the ARC with a metal bomb, and the 5-factor is going to increase a lot higher, and you've kind of lost the benefits of using the ARSST in the first place. So as I said before, the containment vessel around the glass vessel, it can be pressurized with gas to suppress boiling. this is due to it being an open system, the high pressure is all around the glass vessel and it doesn't cause it to break. That also means any pressure increases from the decomposition are contained with that whole containment vessel. There is direct heating between a heater belt to the glass vessel wall, so there is very little in between the heater and the sample material as well. So as we've said, this was kind of designed for and favors gassy systems, and it can be used as a sort of a minimum best practice for vent sizing equations. Moving on from the AirSST, we get to the VSP2, the vent sizing package 2. Again, this is a Fauski instrument developed and preferred by the DEERS for emergency relief systems. This can again be used for thermal stability testing in much the same way as the AirSST, but there is a larger sample requirement. We need sort of 50 to 150 grams. Again, this system is very adaptable for the kind of testing that you need to do, whether it be basic thermal stability testing or actual desired reaction calorimetry. But for this aspect, just thermal stability, we may advise using this if the reaction mixture is very complex and we're not confident we can get a representative mixture into, say, the AirSST, and you still need the vent sizing data. So these systems can work in various different modes, but for thermal stability assessment, it would normally be the constant ramping mode. And again, this is a very low phi factor system, particularly if you're using it in the open cell function, just the same as the AirSST. So it's very similar to the way it works to the AirSST. It's just a larger system. So the containment vessel there is 4 litre volume rather than 330 mil. And again, it has direct heating. A heater belt is wrapped around the containment vessel, and it heats the material directly. So there are other systems on the market, ones that we've not discussed, but they all give very similar data typically. So we've got the thermal screening unit, the Calvit C80, EV+, the Phytech. These all kind of give similar data, but they tend to sit in line with the tests that we have for different stages and different scenarios of reaction. And as I've kind of said a little bit, all of this data needs to tie in with the desired process. So that's where reaction calorimetry comes in. And this reaction calorimetry testing can be performed in a range of equipment depending on what's most appropriate to the process being tested. So we've got lined up there sort of the Phytech, VSP2, those will be used if vent sizing is required. And then we have a reaction calorimeter for sort of atmospheric systems. And the reason we need to consider these different tests in conjunction with each other is just outlined a little bit here. So the application of thermal stability CRH data, we've got a scenario here where we've got our normal process in stage 1 at the bottom. We've got a exotherm as we go through time, which we are anticipating. But then there is an occasion where we have a cooling failure at 0.4, and we then have an increase in temperature. So that is the temperature from being output from the desired reaction, but you're no longer taking that heat from the system because the cooling has failed. So you get to the point which is MTSR, and that's the maximum temperature of your synthetic reaction. And the reaction is sort of tailing off at that point. But you can find that you may then trigger a secondary reaction, which is the darker grey block in the top right corner, and that is where your desired reaction has unfortunately triggered a secondary decomposition, which has its own exothermic output, and again increases the temperature to a high level. So these can be classified under several different classes, which is all kind of based on what's the theoretical, the maximum temperature of your desired reaction, what is the maximum theoretical temperature of your system based on boiling points and containment of the reaction mass, what kind of temperature you might start triggering decompositions, and the combination of those will define the reaction into different criticality classes there. So just to summarize a little bit of the webinar here, so we've sort of defined what thermal stability is in regards to chemical reaction hazards, and what we mean by the differences between screening techniques and adiabatic techniques, how pressure and temperature hazards can cause a risk to thermal runaway, examples of thermal runaway or other chemical reaction hazards, and what other causes there might be for these incidents, why these need to be taken in consideration when designing a new process or making a change to a chemical process, and the potential causes for these kind of events and scale-up issues. And again, key to the testing are kind of the phi factor, the correction factor, the difference between small and large scale, the different screening thermal stability techniques available are adiabatic testing techniques, the differences between considering your desired synthesis and potential upset conditions, and how it all links into proper reactor and vent design. So thank you very much again for joining us today. We've got our details there for getting hold of us at Sigma-HSE in the UK. We'll always welcome any contacts or any queries you have. Thanks very much.